All right. Hello, everybody. I actually got a really cool question from one of our students. And as always, I wanted to make sure that if one person has a question, then many other folks may have the exact same question. And it was a really insightful, a really good question. Um, so what I'm going to do is I'm going to share some of the questions and then try to go over the answers rather than go over one person and another person, then another person. Normally I would put this in discussion boards, but I found that this type of thing, I like to see it better, and hopefully this will explain it. So I'm going to share the initial question. And so you should be able to see my screen right now. And the question was as follows. And it was, according to page 278 in our reading, why is it that when light travels through the second medium, it bends away from the normal this time? It was a homework, and what was happening is, remember, we've covered this situation where light goes from, let's say this was air, and I'll insert text box, and up here, and we'll have this in front of. It's going from air, which is an index of, let's call it 1 for our purposes. And let's go into this one where let's call this, say, CR39, which has an index of, say, 1.50. And remember, all that means is that when light travels in a vacuum or in air for our purposes, it travels 50%, it travels slower. So in this case, if it's coming in at 300 million meters per second, if it hits CR39, it's going to be going around 200 million meters per second. It slows down. And remember, 300 divided by 200 is 1.5, so that would give us our index of refraction. And normally we would have expected the light to hit here, and if it didn't run into anything, it would have continued to go down here. However, it's slowed down. That's how refraction works. Remember, some is reflected, some may be absorbed, but the majority of it is simply going to be refracted. And when light goes from a faster speed, light in air, to a slower speed, light in the medium, it bends or refracts towards the normal here. Now, again, if light travels from a lower index to a higher index, it slows down relative to how it was moving before. Going fast, going slower, bends in. So in this case, it's refracted or bent toward the normal. But if we went from, and remember, lenses, we wanted to show you how light hits a specific interface, and like if I'm going from air to the lens. But remember, like if I have my eyeglass lenses, my prescription sunglasses right here, light is going to go in from air to my lens, but it's going to spend a small amount of time in the lens, but then it's going to shoot back out again. So it's got to go not just one surface, it's going to hit two surfaces. It has to go through the front of the lens and then come back out the back of the lens. And in this case, let's say if the light was going from an index that is higher, say in this case it's the CR39 that it's coming back out of, back into the air, here, notice how we're going slower, and then it should have gone this way, but since it's going back out into air and it's going to go back to its original speed, 300 million meters per second, if it's going from slower to faster, it no longer bends towards the normal, it bends away from the normal. And so this is how light, it slows down, gets closer, it speeds up, it gets farther away. And so this is how light would actually work. And so hopefully if you play with, and let's go back into our exercise, this here, this was in our homework, in our lab exercise. And so if I hit this here and it's going straight down among the normal, remember our formula was simply sine the index of the first material I'm coming from, and if I take this angle from where the angle is entering to the normal and measure that in degrees and take the sine function on my calculator, And then that should equal whatever this index is, and then the sine of this angle from this light to this normal. And that's literally Snell's law. So I can figure out a couple things. If I tell you what it's coming from and what it's going to, and I give you one angle, you can find the other. If I give you two angles and I give you one index, you can find the other. This is just plug and chug when we come to basic algebra. And although there's a sign key in there, you don't have to understand what the sign means. You just need to know how to use it on your calculator. Now, let's use this in here. So if I have sine of, let's say it's coming from air going into plastic, 1.50 plastic. If it comes in and the light is here, I'm going to see some reflected. This angle and this angle are the same, but this looks like it should have been going here, and we went towards a normal. It went slower. It refracted. It bent towards the normal. But what's neat is if I come at an angle that's exactly dead on, this hits here and it still slows down, but it doesn't change direction because it's coming in perpendicular. It's going to leave perpendicular. It won't bend. It's only when I'm coming in at an angle that this actually will refract and change. It still changes speed, but it doesn't change direction. And this is sort of important. But notice how I can really get a significant amount of bending here. It looks like it should have gone this way, but it really bent in. And I'll actually take this, I'll take a photograph of this, and I'll put it on our little worksheet that we're working on right here. It appears to me, and I'll hopefully prove it to you, that it looks like it should have been going this way, but instead it bent towards the normal. So this angle was our angle that it's coming in, angle incident, and then this is the angle that it's refracted. If I knew this and the index, and so this is how going from a faster speed like air to plastic, it slows down and bends in towards the normal. However, all bets are off, and the exact opposite happens when we're going from, say we're going from glass back to air. Let's go up here for a second. So now take a look at this. If we come in here, this looks like it should have been going this way. It's coming from plastic or glass. It's a higher index material. And as I come in, if I come in, I come in, I come in. As I exit, it should have been going this way, but look what happened. This time I'm going from a so in this case, lower index, such as air, into plastic, 1.50. For all our purposes. But then if I do this one instead, and I'm going to go from the plastic back into air, it's going from a higher index of refraction to a lower. We'll take a look now, and in this case, it looks like it should have been coming out this direction had we not refracted it. It looks like it should have gone here, but notice this time, because we're going from a higher index to a lower, now it's actually bent out. Stop that. Now it's bending away from the normal. So this is one of those questions where we're not dealing with, I just wanted to show you how light goes into a single surface, but it's this is how, like on a prism, if you were to look at the prism, if I have one of those. So if I were to have this original one here, light comes in to the plastic, and then it's going to, oh, where's my, I have to get a better one. So yeah, let's not use this one if you don't mind. Well, I'll keep it at that for now. So I'll draw a whole prism back out if you want, but this is the whole reason why if we have two flat surfaces, light comes in and it's refracted at the first interface and then refracted at the second interface. And this is if we draw it out like we did in class briefly for the handout, that's why light bends towards the base of a prism. So now let me go on to the second thing that this student pointed out. And they said on page 278, it says light passes perpendicular through a medium. It doesn't deviate. However, when it passes through a second medium, the book says the angle strikes at an equal angle to the tilt of the second tilt. What does that mean? Is light supposed to be parallel with the new medium? So this may have been confusing, but we call this the apical angle. And right here, I'll draw this out. I can measure any prism that I want. And this angle here, if this is the apex, this is the base, and I have a flatter, a base here and a pointy part here, I should actually be able to measure this in degrees, the apical angle. Well, I'm going to argue that if I have light that comes in specifically perpendicular to the surface, the first surface, if I hit here, this is coming in perpendicular. And we just showed you that if I hit here, it still slows down, but it's not deviated, if that makes sense. But now if I hit here, it turns out that if you see this angle here, I'm going to argue that this angle right here is the same as that angle right there. And let me show you. So let's go through this. So this is our angle. Now this has to have a right angle. So this is right here, a right angle. If light comes along here perpendicular, it comes in at a right angle, it comes in perpendicular. This is the same as coming in on the normal, or the angle of incidence is 0. So the angle that's refracted, even though it slows down, it's not deviated. It comes out perpendicular. So now it's going to go straight through here. There's no change. But it's going to hit here. And what I want to do is I want to measure, taking this piece right here. I want to have this dotted red line is called the normal, this perpendicular. I need to figure out what this angle is from the angle that's incident to the angle of normal. I need to find this angle right here. And how would I do that? And if I do that, if I know the index, let's say it's a plastic lens, let's say it's in light, in air, I should be able to, if I know this angle, that's right, duplicate, draw here, here. If I know this angle, then I should be able to, and remember, it's going from a higher index to a lower, so it's not going to continue here. It's going to go, stop that. It's going to go away from the normal because it's going to a lower index. So I should be able to measure this here. Angle of the incident from a higher index to a lower index. I should be able to figure this out. Now, so here it is, and then there's the normal. If I know the normal, I should be able to figure out where it's going to go from where the light was originally going. It's going to bend this way. So I want to be able to calculate this out. So how would I do that? I need to be able to figure out what this angle is right here. Well, let's extend this so that I made a triangle. And look, I have now this triangle. Here's the top of the triangle to where the light enters to right here. That's a 90-degree triangle. But I now have just formed another triangle. Here's 90 degrees. And I would hope that you would expect that this is a right angle and that this is a right angle. These are two right angle triangles. But what's interesting here is this right here, where the normal is, by definition, it is now perpendicular to this surface here, which means that is also a right angle. And remember, by definition, let me put this in here, insert text box, all triangles have three angles and cool. So in this case, I would hope that you are familiar with, from this triangle, this is 90 degrees, 90 here, and the whole triangle is 180 degrees with one right angle. That would have to mean that this apical angle and this angle right, let me draw this out, that would mean that if this right angle right here was 90, these two angles are exactly the same. I would argue that if the whole triangle from here, let's draw from here, 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 and it's 90 degrees. And let's just call this apical angle, let's say it's 30. That would mean that this angle right here is 60. But that would mean if this angle is a right angle, because the normal is 90 degrees, but if I knew that this is 60 from the bigger triangle, that would mean this angle right here is 30. So that means if I'm looking at this diagram right here, whatever this apical angle is, and this is the apical angle, and in this case, call it 30 degrees. If I come in straight into the first interface right here at a 90 degrees angle, it's going to go in straight, it's going to come out straight, it's not going to be refracted. Once it hits here, if I draw this normal, I'm telling you that this right here, the angle of incidence, is now also 30 degrees. So when I start doing my Snell's law, I can ignore the first one because it wasn't refracted, and whatever this angle is here, this angle is also the same as whatever this is. So if they give you like 15 degrees is the apical angle, then the angle of incidence for this here, the 15 would go here. In this case, I gave you 30 degrees up here for the apical angle. That means when I'm doing my N1 over sine theta 1 equals going the index 2 times sine theta 2, or this is the incident versus the reflect, then I know in this case, let's say this was plastic, and this is air. Let me back out into air. I know that this here would be, coming from the plastic, would be 1.51, 1.50 is the index times a sine of 30 degrees equals 1 times a sine, and in this case it would be 1.5 times the sine of 30 is 0.5 if you're doing degrees, equals sine of angle 2. And so now I would actually be able to calculate this all out. And so now the sine of this angle is 0.75, so I can just find the inverse if you want to. And again, this, I won't ask anything quite this difficult, but where's my other? I don't have an inverse sign here, do I? All right, let's do 0.75. Oop. So this would be coming back out. Oop. Would be about 49 degrees. And then if you see where it would have gone, and again, this gets a little messy, but if you were to if it were continue here, you would have actually had it change by that amount right there. It would have continued in, and we would have diverged it down, it would have gone down by about 19 degrees. That way, you can actually look at how much it's going to bend towards the base. And if I do this, draw here. And so this is just a fancy way of essentially showing you I came in here, didn't move, hit here. I know what this angle is because the apical angle and this, the angle of incidence, is the same, and I can figure out how much it's gone away from the normal because you're going from a higher index to a lower index, and that's what it meant by that. And all it meant in a long, if you got nothing out of this particular part, this angle, if it comes in here, if you come in parallel, perpendicular to the surface, whatever this angle is, that's what the angle of incidence is. And the apical angle gives you, instead of, that's a way for you to, if it came in any other way, I'd have to calculate this one, and then it'd shift, and then it'd come back down, and I have to do two different angles. This one makes it so there's only one calculation. And that was what the apical angle was trying to explain. And then finally, lastly, and this is what I really like, there. Lastly, it says light refracting off the base. Lastly, it says light reflecting off the second medium now bounces away from it. So that was what we were just talking about right there. So lastly, it says light reflecting off a second medium now bounces away from the normal line because it's going from denser space. But what if it's going from dense to even denser medium? This is the question. What happens if this goes from a dense to an even denser medium? And I think that's an absolutely brilliant question because we're not always dealing with air. So let's look at this. It's the difference between the two medium that make a difference. We've been talking about going from air into water. Or we've done air into polycarbonate. However, let's take an example. You make a set of swim goggles. They are specific prescription. When light travels from air to the polycarbonate lenses, for example, they're going to bend a specific way. They're coming from 1 to 1.586, so it's expected to refract a specific way. But what if we're in a swimming pool? Now, we're going from water into the polycarb. We're not dealing with 1 into poly, like an index of 1 into 1.586. We're talking about 1.33 into 1.586. And so now the question is, how is it going to bend? Is it going to bend bend away? Well, in this case, if it is going from lower to higher, it bends towards the normal. So this will still bend towards the normal, but the difference, it's going from 133, water instead of air, it's not going to bend as much. So if we plug this into here, let's look at how much. We'll do air into polycarbonate. And if you can see how much it bends right there, what happens if I change this to water? And be very careful of this here. You're going to see that it should be going this way, but it's going to bend in towards the normal, low to high. It's going to be bending towards the normal. But if I change this, you're going to see that if I change the index from air to water, this is going to stop bending quite as much. Watch what happens. See how it's going back towards where it came from. It's still bending, but not as much. This would be air, it bends better, air into poly, water into poly. It's refracting, but not as much. And this is important because if I have a pair of swim goggles and I look underwater, the prescription as it goes from the water into the polycarbonate lenses is not going to be as effective a refracting surface as it would be outside. It changes prescription a little bit. That's a little bit deeper than what I want to get into for this class, but at least understand the principle behind it. So again, to my student who brought up these questions, brilliant questions, love them, definitely means that you're paying attention, and hopefully being able to look at this in 3 different parts. The apical angle, the going from low to high versus high to low, and then the different indices, like say water to polycarbonate, rather than just always being in air. Hopefully that'll clear up a few things for you. So appreciate it, and I'll post this and talk to you in a bit. Bye.